Greetings, I'm Salvador Cordova. Welcome to Lecture 1.4 entitled Measurements in this college-level general chemistry lecture series presented by the Evidence Reasons Academy. Thank you for joining me today. Recently, in the course of my professional work, I realized I needed retraining in the subjects I once studied in school, but now had mostly forgotten. I needed retraining so I could be more effective in my work. One way to learn or relearn something is to teach it. I realized that by making teaching videos, I could relearn much of what I need to relearn, but I could also help others in the process. And that is why I'm making video lectures like the one I'm giving today. The material covered in this video is almost verbatim from the OpenStax General Chemistry book 2E and is reproduced here in this video under a Creative Commons License 4.0 as detailed in the video description. In my opinion, what is offered in these free videos is worth far more than an entire bachelor's degree in certain disciplines. At certain universities which charge over $250,000 to get a bachelor's degree, in certain so-called social science disciplines of questionable scholarly value. With that, let's dive right into Lecture 1.4 entitled Measurements from OpenStax. Lecture 1.4, Measurements. Learning Objectives. By the end of this section, you will be able to explain the process of measurement, identify the three basic parts of a quantity, describe the properties and units of length, mass, volume, density, temperature, and time, perform basic unit calculations and conversions in the metric and other unit systems. Measurements provide much of the information that informs the hypotheses, theories, and laws describing the behavior of matter and energy in both the macroscopic and microscopic domains of chemistry. Every measurement provides three kinds of information: the size or magnitude of the measurement, a number, a standard of comparison for the measurement, a unit, and an indication of the uncertainty of the measurement. While the number and unit are explicitly represented when a quantity is written, the uncertainty is an aspect of the measurement result that is more implicitly represented and will be discussed later. The number in the measurement can be represented in different ways, including decimal form and scientific notation. Scientific notation is also known as exponential notation. A review of this topic can be found in Appendix B. For example, the maximum takeoff weight of a Boeing 777-200ER airliner is 298,000 kilograms, which can also be written as 2.98 times 10 to the fifth power kilograms. The mass of the average mosquito is about 0.000025 kilograms, which can be written as 2.5 times 10 to the minus 6 kilograms. Units such as liters, pounds, and centimeters are the standards of comparison for measurements. A 2-liter bottle of a soft drink contains a volume of beverage that is twice that of the accepted volume of 1 liter. The meat used to prepare a 0.25 pound hamburger, that's a quarter pounder, weighs 1/4 as much as the accepted weight of 1 pound. Without units, a number can be meaningless, confusing, or possibly life-threatening. Suppose a doctor prescribes phenobarbital to control a patient's seizures and states the dosage of 100 without specifying units. Not only will this be confusing to the medical professional giving the dose, but the consequences can be dire. 100 milligrams given 3 times per day can be effective as an anticonvulsant, but a single dose of 100 grams is more than 10 times the lethal amount. Just a little complaint about the wording here. This thing of a 2-liter bottle of soft drink contains a volume of beverage that is twice that of the accepted volume of 1 liter. I think that's just confusing. I mean, something's 1 liter, 2 liters. That's not, I don't think that's that hard. And so that's just my comment. The measurement units for 7 fundamental properties, base units, are listed in table 1.2, and we'll cover table 1.2. The standards for these units are fixed by international agreement, and they are called the International System of Units, or SI units, from the French Les Estimes International de Units. I don't speak French, sorry. SI units have been used by the United States National Institutes of Standards and Technology since 1964. Units for other properties may be derived from these 7 base units. So the base units are, and this, let me just confirm, this is table 1.2. Length, and that it's measured in meters, and the symbol is M. Mass is measured in kilograms, kg. Time is measured in seconds, and the symbol is S. Temperature in Kelvin, and the symbol is capital K. Electric current, ampere, and that's symbol capital A. Amount of substance, a mole, and it's represented with MOL. Luminous intensity, candela, and that's represented with CD, and that's table 1.2. Everyday measurement units are often defined as fractions or multiples of other units. Milk is commonly packaged in containers of 1 gallon, 4 quarts, and 1 quart is 0.25 gallons, and 1 pint is 0.5 quart. This same approach is used with SI units, but these fractions or multiples are always powers of 10. Functional or multiple SI units are named using a prefix in the name of the base unit. For example, a length of 1,000 meters is called a kilometer because the prefix kilo means 1,000, which in scientific notation is 10 to the third. 1 kilometer equals 1,000 meters, or 10 to the third meters. The prefixes used and the powers to which 10 are raised are listed in table 1.3. So common unit prefixes. Femto, symbol F, 10 to the minus 15th. And there is 1 femtosecond there. I'm not going to be saying, spouting off all the zeros. I'll probably miss one. Pico is symbol P. The factor is 10 to the minus 12th. And example is 1 picometer. Nano is symbol N, 10 to the minus 9th. And an example is 4 nanograms. Micro, the symbol mu, that's a Greek letter, 10 to the minus 6, or 1 microliter, 1 microliter. Milli, symbol M, is 10 to the minus 3, 2 millimoles, 2 millimoles. And that's 2 times 10 to the minus 3. Centi, symbols lowercase c, 10 to the minus 2. So we can have, like, for example, 7 centimeters. Deci, symbol lowercase d, 10 to the minus 1, 1 deciliter. Kilo, with a K, 10 to the third, 1 kilometer. Mega, capital M, 10 to the 6th, 3 megahertz. Giga, G, 10 to the 9th, 8 gigayears. Tera, capital T, 10 to the 12th. An example is 5 terawatts. So now, link to learning. Need a refresher or more practice with scientific notation? Visit this site, and there is a hyperlink there. And you can go to the OpenStax book, and you can find this chapter through OpenStax. Visit this site to go over basics of scientific notation. SI base units. The initial units of the metric system, which eventually evolved into the SI system, were established in France during the French Revolution. The original standards for the meter and the kilogram were adopted there in 1799 and eventually by other countries. This section introduces 4 of the SI base units commonly used in chemistry. Other SI units will be introduced in subsequent chapters. Length. The standard unit of length in both the SI and original metric system is the meter, m. A meter was originally specified as 1/10,000,000th of the distance from the North Pole to the equator. It is now defined as the distance light in a vacuum travels in 1/299,792,458 of a second. A meter is about 3 inches longer than a yard, and there's figure 1.3, which we'll cover. 1 meter is 39.37 inches, or 1.094 yards. Long distances are often reported in kilometers. 1 kilometer equals 1,000 meters, or 10 to the third meters, where shorter distances can be reported in centimeters. 1 centimeter equals 0.01 meters, or 10 to the minus 2 meters, or millimeters. 1 millimeter is 0.001 meters, which equals 10 to the minus third meters. So figure 1.3, the relative lengths of 1 meter, 1 yard, 1 centimeter, and 1 inch are shown, not actual size, as well as comparisons of 2.54 centimeters and 1 inch, and 1 meter and 1.094 yards. So 1 meter is a little longer than a yard, and we have 1 centimeter. 1 inch is 2.54 centimeters. Mass. The standard unit of mass in the SI system is the kilogram. The kilogram was previously defined by the International Union of Pure and Applied Chemistry, IUPAC, as the mass of a specific reference object. This object was originally 1 liter of pure water, and more recently it was a metal cylinder made from a platinum iridium alloy with a height and diameter of 39 millimeters, figure 1.24, which we'll take a look at. In May 2019, this definition was changed to the one that is based instead on precisely measured values of several fundamental physical constants. 1 kilogram is about 2.2 pounds. The gram is exactly equal to 1/1000th of the mass of the kilogram, 10 to the minus third kilograms. So this replica prototype kilogram, as previously defined, is housed in the National Institutes of Standards and Technology in Maryland. Remarkable. Temperature. Temperature is an intensive property. We covered intensive properties in one of the earlier chapters. The SI unit of temperature is the Kelvin. The IUPAC convention is to use Kelvin, all lowercase, for the word, K uppercase for the unit symbol, and neither word degree nor the degree symbol. The degree Celsius, degree C, is also allowed in the SI system, with both the word degree and the degree symbol used for Celsius measurements. Celsius degrees are the same magnitude as those of Kelvin, but the two scales place their zeros in different places. Water freezes at 273.15 K, or 0 degrees Celsius, and boils at 373.15 K, 100 degrees Celsius. By definition, by definition, and normal human body temperature is approximately 300 K or 37 degrees Celsius. The conversion between these units and the Fahrenheit scale will be discussed later in this chapter. Time. The SI base unit of time is the second. Small and large time intervals can be expressed with the appropriate prefixes. For example, 3 microseconds equals 0.000003 seconds equals 3 times 10 to the minus 6, and 5 megaseconds equals 5 million seconds, or 5 times 10 to the 6 seconds. Alternatively, hours, days, and years can be used. Derived SI units. We can derive many units from the 7 SI base units. For example, we can use the base unit of length to define a unit of volume, the base units of mass and length to define density. Volume is the measure of the amount of space occupied by an object. The standard SI unit of volume is defined by the base unit of length, figure 1.25, which we'll take a look at. The standard volume is a cubic meter, a cube with an edge length of exactly 1 meter. To dispense a cubic meter of water, we could build a cubic box with edge lengths of exactly 1 meter. This box would hold a cubic meter of water or any other substance. A more commonly used unit of volume is derived from the decimeter, or 0.1 meters or 10 centimeters. A cube with edge lengths of exactly 1 decimeter contains a volume of 1 cubic decimeter. A liter is the more common name for the cubic decimeter. A liter is about 1.06 quarts. I didn't know that. A cubic centimeter is the volume of a cube with an edge length of exactly 1 centimeter. The abbreviation cc for cubic centimeter is often used by health professionals. A cubic centimeter is equivalent to a milliliter and is 1/1000th of a liter. So let's look at this diagram, this figure 1.25. The relative volumes are shown for cubes of 1 meter cubed, 1 decimeter cubed, which is 1 liter, and 1 centimeter cubed, 1 milliliter. It's not to scale. That's panel A. The diameter of a dime is compared to the edge length of a 1 cubic centimeter or 1 milliliter cube. I don't know why they put a hyphen there, because that looks like 1 minus a cubic centimeter. So sorry, I just had to point that out. So well, that's just a comparison. Let's just move forward. Density. We use the mass and volume of a substance to determine its density. Thus, the units of density are defined by the base units of mass and length. The density of a substance is the ratio of the mass of a sample of the substance to its volume. The SI unit for density is the kilogram per cubic meter, or kilograms per meter cube. For many situations, however, this is an inconvenient unit, and we often use grams per cubic centimeter, or grams per cubic centimeter, for the densities of solids and liquids, and grams per liter for gases. Although there are exceptions, most liquids and solids have densities that range from about 0.7 grams per cubic centimeter, the density of gasoline, to 19 grams per cubic centimeter, the density of gold. The density of air is about 1.2 grams per liter. Table 1.4 shows the densities of some common substances. Densities of common substances. Solids. Ice is 0.9 grams per centimeter. Oak is 6 to 0.9 grams per cubic centimeter. Iron is 7.9 grams per cubic centimeter. Copper 9.0 grams per cubic centimeter. Lead 11.3 grams per cubic centimeter. Silver 10.5 grams per cubic centimeter. Gold is 19.3 grams per cubic centimeter. Gold's pretty dense. Liquids. Water is 1 gram per cubic centimeter. Ethanol, 0.79 grams per cubic centimeter. Acetone is 0.79 grams per cubic centimeter. Glycerin, 1.26 grams per cubic centimeter. Olive oil, 0.92 grams per cubic centimeter. Gasoline is 0.7 to 0.77 grams per cubic centimeter. And mercury is 13.6 grams per cubic centimeter. So for gases, at 25 degrees Celsius and at 1 atmosphere, dry air is 1.2 grams per liter. Oxygen is 1.31 grams per liter. Nitrogen, 1.14 grams per liter. Carbon dioxide is 1.8 grams per liter. Helium is 0.16 grams per liter. Neon, 0.83 grams per liter. And radon, 9.1 grams per liter. That's interesting. We know helium floats. We know that radon can collect in basements, which can be dangerous. And dry air, oxygen, and nitrogen have very similar densities. That's table 1.4. While there are many ways to determine the density of an object, perhaps the most straightforward method involves separately finding the mass and volume of the object and then dividing the mass by the sample of the mass of the sample by its volume. In the following example, the mass is found directly by weighing, but its volume is found indirectly through length measurements. Example 1.11, calculation of density. Gold in bricks, bars, and coins has been a form of currency for centuries. In order to swindle people into paying for a brick of gold without actually investing in a brick of gold, people have considered filling the centers of hollow gold bricks with lead to fool buyers into thinking that the entire brick is gold. It does not work. Lead is a dense substance, but its density is not as great as that of gold, 19.3 grams per cubic centimeter. What is the density of lead if a cube of lead has an edge length of 2 centimeters and a mass of 90.7 grams? Solution. The density of a substance can be calculated by dividing its mass by its volume. The volume of a cube is calculated by cubing the edge length. So we take the volume of a cube. In this case, it's 2 centimeters. It's a cube that's 2 centimeters on each edge. So we take 2 centimeters times 2 centimeters times 2 centimeters, we get 8 centimeters cubed. Just to point out, the units are also taken to the third power because you multiply the units by themselves 3 times. It's taken to the third power. Density equals mass divided by volume. So we take 90.7 grams divided by 8 cubic centimeters. We get 11 grams per cubic centimeter. We will discuss the reason for rounding the first decimal place in the next section. So check your learning. To 3 decimal places, what is the volume of a cubic centimeter with an edge length of 0.843 centimeters? B, if the cube in part A has a mass of 5.34 grams, what is the density of copper to 2 decimal places? So the answers are 0.599 cubic centimeters for A and 0.891 cubic centimeters for B. Maybe just to do this, I'm going to bring out a spreadsheet and I'll do my best for those who aren't familiar with spreadsheets. There are a variety of spreadsheets available through OpenOffice or LibreOffice or even Microsoft Excel. if one doesn't have a spreadsheet, one can use a calculator, but I'll show how I do it with a spreadsheet. So let's do A first. Okay, so we have 0.83843, and that's centimeters. So let's cube this. So I can just multiply. There are a variety of ways to do this. One, I could just use this function called power, and I take that 0.843 in cell B1 and raise it to the third power, and it's that number. And I don't think that can easily be, I've never tried this, power CM. See if it'll let me do it this way. Probably gave me an error. It didn't like me doing that. So units, you'll just have to do that in your head. It's not hard. So the number that I got was 0.599 and some more numbers beyond the decimal place. They said just to 3 decimal places, and that would be 0.599. So I can do that to 3 decimal places. 3 decimal places, 3 places after the decimal point. So now let's do B. And the mass was 5.34 grams. So that's 5.34 grams. And we were assuming how many? 8 cubic centimeters. So it says if a cube in part A is copper, okay, so if the cube in part A is the cube in part A is 0.599 cubic centimeters, and it's a mass of 5.34 grams. We divide the mass by the volume. So the volume is still this. We can divide the mass, which is 5.34, that divided by the volume. And we end up with 8.91 and some more numbers after the decimal place. That would be in grams per cubic centimeter. I don't really have a way of doing superscripts very nicely in my spreadsheet program. So let's see what the answer was. 8.91 grams per centimeter if we go to 2 decimal places. So that's how I did it. I hope that was clear enough. Anyway, let's move forward. Link to learning. To learn more about the relationship between mass and volume, mass, volume, and density, use this interactive simulator, and you'll to explore the density of different materials like wood, ice, brick, and aluminum. And again, one can go to this OpenStax book, and then you can click on the hyperlink there. Example 1.2, using displacement of water to determine density. This PhET simulation illustrates another way to determine density using displacement of water. Determine the density of the red and yellow blocks. I've never done this. Let's see what this simulation is like. Don't know if it's going to blow up. At least Flash Player 8 required to run the simulation. No Flash Player detected. So I'm because they're appeal to this PhET simulator, I'm just going to pause the recorder and see if I can load this Adobe Flash Player. Okay, I'm back. I tried to run this PhET simulation, and Adobe gave me a warning and saying they no longer support Flash Player. So I guess this example 1.2 is dead in the water. So we're just not going to do it. There are other ways we can learn this. So we'll skip it. And that's it for the lecture. Summarizing, and thank you all for bearing with me up until this point. This wasn't the most exciting material, and I don't feel that it was as well worded or presented as could be done, but you get what you pay for. So the learning objectives, again, by the end of this section, you will be able to explain the process of measurement, identify the three basic parts of a quantity, describe the properties and units of length, mass, volume, density, temperature, and time, perform basic unit calculations and conversions in the metric and other unit systems. So I don't think they actually explained the process of measurement. I'm sorry. And what are the three? Identify the basic parts of a quantity. Let me just. Okay, every measurement provides three kinds of information: the size or magnitude of the measurement, a number, a standard comparison for the measurement. You see, I don't think they need to say that. They just have to say unit, not a standard comparison for the measurement. I'm sorry. All they have to do is just say a unit, and I think people can figure it out. And an indication of the uncertainty of the measurement. So just my little bit of complaints, but other than that, I think I don't have any more major objections to the text. So with that, thank you for joining this lecture today on measurements, lecture 1.4. Take care and God bless you.